Have you ever wondered why AI seems to make biased decisions? In today's world of artificial intelligence, we often hear about AI systems showing unexpected biases, from unfair hiring practices to discriminatory loan approvals. The answer to why this happens lies in AI's simplest building block, the perceptron. Today we'll explore how these fundamental units work, how bias creeps in, and most importantly, what we can do about it. Understanding this is crucial for building the fair and ethical AI systems our future demands. Think of a neuron as AI's decision-making muscle. Just like our brain's neurons, it takes multiple inputs, weighs their importance, and makes decisions. Here's how it works. These input nodes receive different pieces of information. Each connection has a weight. Think of it as how important the input is in the final decision-making process. There's also bias nodes, which act like a threshold for making decisions. Finally, the activation function determines the final yes or no output. Let's see how perceptrons learn using a real-world example. Imagine training an AI to sort job applications. The perceptron receives various inputs like years of experience, education level, and skills. During its training, it adjusts its weights based on whether its decisions were correct or not. If it makes a mistake, it tweaks these weights to do better next time. The bias term helps fine-tune where the decision's boundaries should be, like setting a minimum threshold for qualification. Watch how the decision boundary shifts as the perceptron learns from more examples. Bias can enter the system in three major ways. First, through training data bias. If the historic hiring data mostly shows male candidates, the perceptron will learn to favor male applicants. It's the classic garbage in, garbage out principle. Second, we have feature selection bias. If we're only looking at certain characteristics while ignoring others, we are building blind spots into our system. As an example, focusing solely on university rankings might disadvantage qualified applicants from less prestigious schools. Third and finally, we have historic data reflection. Past discriminatory practices become encoded in the weights themselves. Look at how these historic patterns create a feedback loop that perpetuates existing biases. What starts off as small bias doesn't stay small for long. Through feedback loops and reinforcement, these biases get amplified over time. Watch this visualization of the snowball effect. Each decision influences future training data, which leads to stronger biases, which affects more decisions, creating a cascading effect. A slight initial preference can quickly become strong systematic bias. This is particularly dangerous because it can make bias appear to be validated by data, when in reality, it's just amplifying existing prejudices. Let's explore how neural networks with multiple layers can actually amplify bias in ways that we might not expect. Here we have a typical neural network. It consists of an input layer in blue, two hidden layers in green, and an output layer in red. Each layer contains multiple nodes of artificial neurons. These nodes are all interconnected, with each connection carrying a weight that can either amplify or dampen the signal that's passing through them. Information flows from the input layer through the hidden layers and finally to the output layer where decisions are made. Now let's track how bias can flow through this network. Watch the yellow path. It shows one possible route for bias to travel through the system. The process happens in three steps. First, we start with the initial bias in the input data. Then the bias gets amplified as it passes through each hidden layer. Finally, these effects compound when we reach the output. Let's put some numbers to this. At each layer, the bias gets multiplied. By 1.5 at the first layer, 2.0 at the second layer, and 2.5 at the third. This might seem like small increases, but watch what happens. The final result is that our initial bias has been multiplied by 7.5 times. This is only a simplified example. In a real neural network with hundreds of layers, the amplification can be much more dramatic. Understanding this amplification effect is crucial to developing strategies to prevent bias in modern AI systems, especially in large language models where the effects can cascade through millions of parameters. This is why even small biases in our initial data or model can lead to significantly biased outputs in the final system. These biases have serious real-world consequences. In hiring algorithms, qualified candidates get filtered out based on historic patterns. Loan approval systems may discriminate against certain neighborhoods or communities, and facial recognition systems show lower accuracy for minorities and women. Even in healthcare, AI systems can show reduced accuracy in diagnosing conditions for certain demographic groups. These aren't just technical issues, they're affecting real people's lives every single day. But there is hope. We can address these issues through several key strategies. First, ensuring that our data is balanced and representative. Second, by carefully selecting and validating input features. And third, implementing regular bias audits to catch problems early. Fourth, maintaining meaningful human oversight of AI decisions. And finally, building diverse development teams who can spot potential bias before they become problems. Each of these solutions plays a critical role in creating fair AI systems. Understanding how perceptrons can amplify bias is the first step towards building better AI systems. As we've seen, small biases can quickly become significant problems, but with proper awareness and the right mitigation strategies, we can create AI systems that are both powerful and fair. The future of AI depends on the ability to understand and address these fundamental issues. So let's commit to building AI systems that work fairly for everyone.